This lecture series I'm going to be calling Baby Real Analysis. I just put baby in quotes just because this is going to be I would say, less complicated version of real analysis, more of like an introductory real analysis. And this will be lecture 1A. And as far as the texts, there's going to be 3 textbooks that I'll be using. The first 2 are the ones I'll probably use the most. The first textbook's Introduction to Real Analysis, by 4th edition by Bartle. And the second textbook is Real Analysis, a long-form mathematics textbook by Cummings. So these 2 I'll be using frequently. And the third one is Principles of Mathematical Analysis, 3rd edition, Rudin. And that's been nicknamed Baby Rudin. So the intention or goal for this course was that I wanted to make a introductory real analysis course, but it wasn't on the same difficulty as going just through the entire text, or maybe just going through chapters from the text of Principles of Mathematical Analysis. So not in the same difficulty as Baby Rudin, but I mean, there'll be some problems taken from that, and so it'll be a little bit less difficult, but we'll pull mostly from the first 2 texts. So the difficulty, I would say this is like an upper level undergrad course, and I'm going to assume you have some prerequisite knowledge into set theory. So you're familiar with set theory, the notation for set theory, and you have experience writing some basic proofs. All right. So for our course, so in Baby Real Analysis, I've written here are just some examples of some sets. And you'll see, again, I'm assuming you are familiar with set notation. So that's for in capital. That's how I'm going to use my natural numbers, is how that's going to be written. And right, that's our set of whole numbers, 1, 2, 3, so forth. I'm not including 0 in the natural numbers. When you start counting, as far as I start with 1. So if I'm going to start with 0, I'll make it its own set, and it'll be the natural numbers union with the element 0. So that's the second thing that's listed. And again, you'd have to know set theory. So that's the natural numbers unioned with the element 0. If I had the negative natural numbers in orange, I abbreviate, or symbolically, I put it as the natural number symbol, but with a negative as the, I guess, the superscript. And so that's -1, -2, -3, -4. So it's just the negative versions of the natural numbers. So the integers, z, is basically the natural numbers unioned with the element 0 unioned with the negative natural numbers. So that is what the set of integers is. So it's like -3, -2, -1, 0, 1, 2, 3, and so forth. And then you have the set of rational numbers q, which is the set of all numbers such that you have a ratio m/n, where m and n are integers, but n can't be 0. So all this is, you should be familiar with this stuff. I just wanted to give some examples of some sets, and that's how I would write them. And for this course, we'll focus on the real numbers, which I'll call it capital R. And I liked this text. That was from Cummings, the second text out of our lists of texts, the Real Analysis, a long-form mathematics textbook. So Cummings says that, quote, "The reals are what you get when you start with the rationals and then add in just enough numbers so that it satisfies the least upper bound property." And that's on page 22 from his text. And I like that. It's because it kind of simplifies it down to focus on, okay, so we have this thing, it's more than just the rational numbers. And then we add in enough numbers such that we satisfy what's called the least upper bound property. So we'll talk about later, I guess in these first couple videos, we're going to talk about the least upper bound property. All right, so the R is an ordered field. And so first I'll just go over some field axioms. And a field, capital F, is a non-empty set that has two binary operations, plus and times, or addition and multiplication, that satisfies the following axioms. And these are axioms that we should be already seen before. We've been dealing with this all since like kindergarten or elementary school. And we have commutative law. We just basically switch the order as far as you adding A plus B is equivalent to B plus A, or A times B is equal to B times A. Then you have distributive law. So A times parentheses B plus C is equal to A times B plus A times C. And then you got the associative law. And again, the upside down to A, all right, that means for all, which in set theory and proof-based course, you should already know that that's for all. And then this is going to be there exists. And then, so these are symbols you should already be familiar with. So for all A, B, and C, and F, for the associative law, we basically switch where we do the grouping of the parentheses, whether we do A plus B in parentheses or group the parentheses around B plus C. And same for multiplication. Then axioms 4 and 5 are the important axioms. One of the identity law. And so you have what's called the additive identity, which is the element 0. So 0 is the additive identity, and it just means if you add any number A plus 0, you get the same number A again. 1 is the multiplicative identity, so similar concept is anytime you take any number A and multiply it with this element 1, you get A again. And then inverse laws. So for all A and F, exists a negative A and F corresponding with that original A and F, such that when you add A plus negative A, you get the additive identity 0. And the second one for axiom 5 is for all A and F, where A is not 0, there exists this thing that says, looks like A to the negative 1 in F, where A times A to the negative 1 is equal to the multiplicative identity 1. And so most of the time we just write A negative 1. It's just 1 over A, right? The reciprocal. So some questions. Is the natural numbers the field? What about the integers? And what about the rationals? Now to answer these, so do they follow the field axioms? So is the natural numbers a field? Let's see. So you can add two natural numbers to get a natural number. Distribution, that would hold. Associative, that holds. But notice there's no element 0 in the natural numbers. And also we don't have these inverse elements where it's negative values. And also reciprocal value. So really, there's multiple reasons why. So this is not a field. The natural numbers is not a field. For instance, 0 is not an element of the natural numbers. All right, so we don't even fails to have the identity law for that case. And then there's also, we don't have negative element, so it fails the inverse law also. Right, because we don't have negative elements such that when we add them to the element that's in N, you still get you get 0. Well, 0 is not even in the natural numbers. And then also when you do a to the negative 1, which is essentially doing 1 over a, you don't have any of those elements in the natural numbers. All right, so we've established that the natural numbers is not a field. Now what about the integers, z? That's also not a field. So why? Well, we fail to have multiplicative inverses. All right, that's just this part of the axiom 5. We don't have that. Now the rationals, Q, is that a field? And it's yes, it follows all of the axioms. All right, so the natural numbers is not a field. For one thing, it doesn't have the element 0. And that is the additive inverse as far as you get a plus negative a, you get 0. So, sorry, it's the 0 itself is the identity element, but we fail to have additive inverses in the natural number such so that when you add a natural number to its additive inverse, you will get 0, which you fail to have 0 and that additive inverse, along with failing to have the multiplicative inverses as well. Now the integers, z has it's not a field, but that's mainly because it doesn't have multiplicative inverses, so like reciprocals. And Q is a field. All right, so that's just axioms for fields. I took these axioms as far as where I cite these. These are all coming from J. Cummings' textbook. I mean, these are understood axioms in mathematics, but I figured the way it's written like this, it's coming, I just wrote it directly coming from J. Cummings' real analysis. So I'm going to be using two texts as my primary two textbooks, and the first one's the Bartle's Real Introduction to Real Analysis, and the second textbook is this J. Cummings textbook, Real Analysis, the long-form mathematics textbook. So these field axioms come from J. Cummings. Okay, so that's fields. Now ordered field, an ordered field axiom. So an ordered field is a field F along with the following additional axiom. So we have those 5 axioms along with the 6th axiom called the order axiom. And again, this is citing it from J. Cummings' textbook. So there's a non-empty subset P. And again, that symbol is what I'll use for subset. And then this the proper subset. So P is contained in F, but P could also be the same cardinality as F, or same set as F. So that's why we have just the subset, and then proper subset. I'll use that if it's needed to specify as a proper subset. So the positive elements such that if A and B are in P, then A plus B is in P, and A times B is in P. So that's just closure. And then the second part for axiom 6 is that if A is in F and A is not 0, then either A is in P or negative A is in P, but not both. All right, so if A is not 0, it's either A is in P or negative A is in P. And this set P is called the positive elements. So definition, if F is an ordered field and A and B are in F, then we say A is less than B, or in parentheses, B is greater than A, if B minus A is in P. Likewise, A less than or equal to B, or B greater than or equal to A, means either A is equal to B, or A is less than B, or correspondingly to the blue part, B is greater than A. So now we've used this ordering to the field, and that provides, just a, so we were dealing with fields at first, but now we're dealing with ordered fields. And now ordered fields, we're calling this thing called A less than B, or in parentheses, B greater than A. And it's based off of the positive elements. So since the real numbers is an ordered field, I'm going to basically focus our attention now on just R itself. And for this, I will be doing some examples. These 4 examples are going to prove, and we'll be using this information that we just learned about the positive elements. And we'll focus our ordered field on exclusively just being the real numbers R, since we're dealing with real analysis. All right, so now we've come to the first set of proofs. So this is the good part. Yeah, so the problem I'll be stated in blue, and then I'll use a different color to work out the problem for the proof. And I'll do the proof in green. So we're dealing with R as our set. Since we've already, I just wanted to talk about a field at first, going over those axioms and then the order axiom, and state that, well, the real numbers is an ordered field. All right, so now we're going to focus our attention on just the real numbers for these examples. So A and B and C are real numbers, is what I'm saying. So for part 1, it says if A is greater than B and B is greater than C, then A is greater than C. So we're trying to prove that. So for our proof, and I'll usually do PF for proof. And this will be proof of 1. So we want to prove A is greater than C. So we're going to assume A is greater than B, B is greater than C. And we want to show A is greater than C. So for we want to show, I'm going to abbreviate that as WTS. So that's how I would say is want to show. And these first proofs, I'm just being, I guess they're not going to be they could be quicker, worded a lot more quicker than how I'm doing it. This is just so to explain sort of the thought process while doing the proof. So it's not the most elegant proof, but I figured it might help to just see how my mind goes as far as trying to break down the proof. So we have the A is greater than B, B is greater than C. We wish to show or want to show that A is greater than C. Now, what does that mean? Well, what does A greater than C mean? So based on our set for positive elements, so we have A less than B, or in parentheses, B is greater than A, if B minus A is an element of B. So A greater than C means that A minus C is an element of the positive elements. All right, that's what we want to show. Okay, so what I'm going to do is I'll start out with A minus C, and this will be sort of the actual proof, I guess. So if I do A minus C, now you can, so a clever thing that you'll see in proofs over and over is what's called adding zero. And by adding zero, I could say A plus 0 minus C, and I'm just doing it to be extra descriptive here. Now, what is 0? Well, we could write 0. We want to make use also of the fact that we have A is greater than B and B is greater than C. So I already have the letters A and B. I want to introduce the letter B somehow. Well, I can do that because I know that 0 is the same thing as plus B minus B, right? So that's what we mean by adding 0. I can write 0 as plus B minus B. Now I want to make use of my assumptions. And by the assumptions, what does A greater than B mean? Well, then that means that B or A minus B is an element of P. And then B greater than C, that means B minus C is an element of P. All right, so I can, by commutativity, I can switch the order so that I have A minus B, or A plus negative B, which is A minus B. So I can switch it so I have A minus B and then B minus C. All right, so first thing is I just brought in the additive identity 0, and I wrote it as B minus B because these are additive inverses that add together to give you 0. And now I'm doing commutativity, just switching the order. So and I won't do this for all proofs, but I figure since this is the very first one I'm doing, I'll be very descriptive. So I've introduced 0. A minus C is equal to A plus 0 minus C because we know 0 is the additive identity. And I could write 0 as positive B minus B because that's just a property of additive inverses. Right? Just any number x plus its inverse negative x is equal to 0. All right, then I just switch the order around using commutative property. And then I can group A minus B and then B minus C. All right, that's associativity. I'm just grouping the A minus B that I'll do, and then the B minus C. Now I can make use of what I know. Well, what is A minus B? So A minus B, we know A is greater than B. All right, so then A minus B is an element of P. So this whole thing, A minus B, that's an element of P because A is greater than B by our assumption. B minus C is an element of P because of our assumption that B is greater than C. So if I have an element that's in P plus another element in P, then the whole thing, A minus C, has to be in P because of closure. So since A minus C equals these two things that are in P, then A minus C has to be in P, right? Because we know if A and B are in P, then A plus B is in P, so the closure aspect. All right, and that's the first proof. I sort of just kind of, I mean, again, I made it longer than what it needed to be, but I figured I'll show the thought process and then doing each step like this, literally step by step, and justifying that with in blue. That's how we get A minus C to be an element of P. And then, so I guess I'm done, right? Because what does this mean? That means A minus B is an element of P, so A is greater than C. All right, so proof's done. Okay, so that's being really descriptive. Here's how I normally will do it, and I'll do the next problem in quicker fashion. So normally I would do it as the following. It's really the same proof, it's just maybe skip a step or two, but I'll do it quicker like the following. The proof, again, we've said A is greater than B, B is greater than C. That's our assumptions. And then I would write down what we need to show. All right, so then I start out with A minus C. And then I could write that as A minus B plus B minus C. That's because, right, I introduced adding 0 in there. And then I could group A minus B and then group together B minus C. And then, well, this is an element of P because A is greater than B. And then this is an element of P because B is greater than C. So therefore, the whole thing has to be in P. Since it can be written as a sum of two elements in P. And that implies that A is greater than C. All right, that's how I would normally do the proof. And again, it's not as descriptive as this, but I figured since that's the first proof, just to write down literally everything I'm saying. Whereas here, that's how I normally would do it. All right, so the second example, I'll do it quicker. So it's if A is greater than B, then A plus C is greater than B plus C. So number 2. So I'll write down the problem. So we want, the problem is A greater than B. Then B, then A plus C is greater than B plus C. All right, so I see it's similar to how I did this proof, where I wanted to show A is greater than C, and then I just wrote it as A minus C being an element of P. Well, this is true if A plus C minus B plus C, so is in P. So I'm going to write it like that. Well, A plus C, and then subtracting as B plus C. So I could, rearrange this so that I know A is greater than B. So what does that mean? That means A minus B is an element of P. Well, because of this subtraction, I could reorder it so it has A minus B, and then plus C minus C. So A minus B, that's an element of P because A is greater than B. And then C minus C, that's 0, right? So then since I have this element of P plus 0, that's going to give me that element in P. So therefore, the whole thing, A plus B minus parentheses B plus C, has to be in P. Which means that A plus C is greater than B plus C. Hope that makes sense. So I didn't write it as descriptive this time. Right, because this equaled A minus B, because 0 makes it go back to this, that, and we know A minus B is in P. All right, the third one, so this is it, proof's done. The third one states if A is greater than B and C is greater than 0, then A times C is greater than B times C. So I would say A times C is greater than B times C. All right, that's what we're going to prove. So if I were to prove this, A times C greater than B times C, what does that mean? So that means BC minus AC, or AC minus BC is an element of P. All right, that's what we're trying to show. So for the proof, start out with AC minus BC. And then I can write this as, so A is greater than B. That means A minus B is an element of P. P is also greater than 0, so then that P is also itself an element of P. So the one thing is I can factor out C, so distribution, reversing the distribution. That's equivalent to A minus B times C. And we know A minus B is an element of P because A is greater than B. And we know C is also in P because it's greater than 0. So we have an element in P times an element in P. That gives me another element in P just by closure. So AC minus BC is in P, right, because of closure. So then that means our AC is greater than B times C. So proof's done. All right, so the fourth one, and this will be the last one for this video. So A is greater than B. This time C is going to be less than 0. Then AC is less than BC. All right, so what is this statement saying? So we know AC less than BC, just to be consistent with the previous examples, I kept using the greater than. So if this is visually, just for me, I think it helps to just write it as BC greater than AC, which means BC minus AC has to be an element of P. All right, that's what we're trying to show. Show that BC minus AC is an element of P. All right, so the proof, so I'll start out with BC minus AC. All right, so BC minus AC, I can factor out C, and that'll give me, so B minus A times C, right, just by the distributive law. And let's see. So if we want to prove this is an element of P, now I have A is greater than B, which means that A minus B is an element of P. And if that's the same thing, so A minus B is the same thing as negative of B minus A. Right, that's the same thing. So I would write this as negative, and then hold on a second. I have this sort of switch. So this is what we know, A greater than B, that means A minus B is an element of P. Here I have B minus A. Now, B minus A, if I switch the order so that I have A minus B and I want to make it equivalent, I need this minus sign. And now I can make use of, well, A minus B is an element of P. So then I have this minus times A minus B, so that it's equivalent to B minus A. All right, and then I can bring the negative with C. So if C is less than 0, that means negative C is greater than 0, which means negative C is in P. All right, so if I bring the negative with C, so I'll have A minus B times negative C. All right, A minus B is in P by our assumption that A is greater than B. Negative C is in P because C was less than 0, so negative C is greater than 0. So I have BC minus AC is equal to a product of two elements that are in P. So that product's going to be in P. It's the two elements that it consists of for the product are in P. All right, so that's if and only if. So that's going to imply that BC minus, so that's going to imply BC is greater than AC, which is the same thing as stating AC less than BC. All right, so that's the proof. I got a little tripped up there, my bad, but I factored out C, so that gave me B minus A times C. Now, I want to use the assumption that A is greater than B, right? So A greater than B means that A minus B is an element of P. But I can write b minus a as negative times a minus b. So then in the parentheses, the a minus b, that's in p. And then I just rearranged it so the negative would be c. And negative c is an element of p since c is assumed to be less than 0. So I've it written as a product of two elements where each element's in p, so that product has to be in p. All right, so that's it for this proof or this example. The next video, and I called this lecture 1A. The next video will be lecture 1B. All right, so this was, I called this lecture 1A. So next video is lecture 1B, and I'll start out with absolute value. All right, I know this is my first video with this, first time I ever tried to teach this kind of course, so I apologize for the sloppiness. I guarantee you with practice, I'm going to get better.